Hi, my name is Kazimedi Hassan. Welcome to the presentation of EEL 6562 Image Processing and Computer Vision. The name of my project is Comparative Analysis of Depth Recovery Techniques for Single Defocused and Stereo Vision Image. First of all, we're going to start with the presentation outline. The first topic I'm going to introduce is the problem formulation of depth recovery. Then we're going to discuss the techniques of depth recovery. Secondly, we're going to talk about the depth estimation from single defocused image, which is one of our principal topic of the project. Under this topic, we will describe the proposed algorithm that we're going to use to estimate the depth, and then we're going to introduce the anisotropic diffusion filtering, the paranormalic scheme, the reverse heat wave equation, and then we're going to combine all these theories, do some simulation, run some code, and discuss the results and observations. The second part of the project is basically the process of depth estimation from stereo vision image. To that extent, first of all, we are going to explain what is the concept of stereophotography and the geometrical setup for one-dimensional projection plane. Then we are going to introduce the concept of image correspondence that is required to figure out the depth estimation. Finally, we are going to run the code in MATLAB and test the code on some various images, present the results, and discuss the observations. The main aim of this project is to discuss the performance evaluation and compare the two techniques. This we're gonna do in one slide. Finally, we're gonna conclude this with some concluding remarks. Um, the problem of depth recovery is basically the concept of depth recovery is basically we have to model an image so the 3D properties of the objects can be extracted from its 2D image. Different characteristics of an object such as texture, shading, motion, shape, these are called the monocular cues, or the stereo correspondence, which are called the binocular cues, are employed to recover depth. Uh, the application of depth recovery we can see in a lot of fields of computer vision and computer graphics. Um, we can use this depth recovery for 3D image reconstruction. It can be used for the image processing in robotics, and in also movies we can use for scene interpretation. So there are a lot of famous techniques for depth recovery. Previously, we said there are the monocular cues, which are the texture, shading, motion, shape, etc. Then we have the binocular cues, which is stereo correspondence, which is like taking two images from two different viewpoints and merge them to get an idea of the depth of the objects in relative to each other. Then there's a process of combining multiple images. There's one more thing called 2.5D maps, which uses the low-level cues to extract information for depth recovery. Some people use active elimination to figure out the depth recovery. In the literature, there also exists the coded aperture method for deforming the defocused blur kernel. Um, then there is the concept of filtering and reverse heat equation for single defocused image. Also, there is a well-known technique which is called the stereo vision image pair. The topic for this project I've chosen to be the last two techniques for depth recovery, and we're gonna go through each section, each of these techniques, the theories, the concept behind it, and then we're gonna run the codes, the simulations, and then we're gonna compare like which technique is best for depth recovery. Um, First of all, the depth estimation from single defocused image. The assumptions that are being taken for measuring the depth from a single image is the relative depth of the objects and the relative distance with each other is being estimated by the blur. The drawback is this is a really weak assumption because we assume that the focus part of the objects are closer to the imaging system and the blurred part of the image is farther away. But in reality, the different focal distances of the camera lens might capture objects situated far away with finer resolution. So these are the drawbacks of our assumptions, but the assumptions that we take based on that, and with the aid of some tools like the partial derivative equation based on continuous image intensity, then application of inhomogeneous reverse equation, anisotropic diffusion filtering, and some simulation tool for MATLAB for this kind of PD, we can actually decode the depth estimation from single defocused image. The first concept that is necessary for estimating the depth in this process is the concept of anisotropic diffusion filtering. This is also known as the Perona-Malik scheme. In 1989, Perona and Malik proposed a novel approach, pioneering work to contravene the anisotropic filter. What this filter does is basically preserve the edges of the image objects, and also at the same time it reduces the noise. The foundation of the anisotropic filtering is known as scale space representation of an image. This is basically a cluster of signals shaped by implementing the diffusion process on the signals. The equation is for the diffusion process is given over here, which is delta u by delta t equals to c delta square u by delta x square plus delta square u divided by delta y square. This equation will be explained later in the presentation. And following that equation, we have some the scale space representation of signal, a figure. The bottom signal is the original signal, and we apply the diffusion process to smooth it out in various time t. So anisotropic filtering, it has three different principles. First of all, we have the causality, which states that any piece at rough level of resolution should persist on a cause at all final level of resolution. Then we have the second principle, which is known as the immediate localization. So each resolution at its edge boundaries must spatially intercept with the causal edges at a final resolution. Finally, we have the piecewise smoothing option, which should be used on the area limited by edges or boundaries. So combining all these three principles, we can finally come out with the final equation for the anisotropic diffusion filtering, which is given at the bottom of the slide. I'm gonna explain it in the next slide. So from this equation, what we can see is that there are some parameters that are of primary interest. First of all comes the diffusion constant C. It is a function of variable x and y, which are spatial dependent, and it's also, if you see, C is also a function of time t. So if C has a greater value at the coordinate points x and y and is not linked with the edges, and it has lesser value at coordinate points that are associated with the edges. So according to that equation, we can state that the gradient value will determine the presence or absence of an edge by identifying a small or great value at the spatial points. So the diffusion constant C is defined as the gradient of the delta function u, which is also a function of spatial coordinates x, y, and time t. The anisotropic filtering additionally have two different functions that are derived for the gradient. The functions are the one is expressed as exponential and one is expressed as reciprocal. So this formulate the partial derivative equations for the anisotropic diffusion filter equation, which is delta u by delta t equals to c xyt, which is the diffusion constant, and then we have the partial derivative, which is del square u by del x square plus del square u by del y square. Further discretization is achieved by the following equation. I'm not going to go through the details over here. So finally, after the discretization and taking the value of del t, del x, and del y to 1, we get the final anisotropic diffusion filtering as the equation uit plus 1 equals to uitj plus gamma and a whole part, which I will explain later. So if you see the constant gamma over here, it's really important to our topic. It's the value of the gamma should always be less than 1. It's also known as the numerical stability, and we're going to discuss it in the next slide. And the following equations that you see, the 8 equations, these are the partial derivatives, and it forms the anisotropic filter, PDE. So these are the analysis and results of paranormalic scheme or the anisotropic filtering scheme. So this is the anisotropic filtering scheme actually depends on three parameters. First of all, we have the stability constant. So stability constant is basically the value of gamma. So we see that gamma should be less than 1, and the larger value of stability constant will result in blurring at intra-region in the image. Well, on the other hand, the smaller values of this constant will delimit the blurring, thus causing noisier image. So after a lot of speculation and MATLAB code running, I figured out that the value of 0.7 can create more accurate blurring. Then we have the function constant, which is denoted at k in the previous slide. So the greater values of it actually distinguishes boundaries from noise, and the greater values of k will detect less edges and preserve them for large amount of blurring. The control value of um, k equals to 40 can create more accurate blurring. Iteration number is also important. More iteration means more, it increases the blurring in the intro region. The drawback of increasing iteration is the higher probability of missing weak edges and thus leading to blurring beyond the edge skills. So after some simulation, I figured out that the iteration of 10 can give a good result of blurring within the edges. The next part of the presentation I'm gonna explain in this second part. Yeah, please refer to the second part for the rest of the presentation. Thank you.